Yeah, welcome back to lecture 27, maximum and minimum values of a function in several variables. This topic in one variable I have already studied in lecture 19 and 20. For the several variables, the method is a little bit different and we will learn the methodology also here. So let's start maxima and minimum values of a function in several variables. Let a function, I am going to discuss here for two variables. Let a function fxy be defined and continuous in some closed and bounded region R. Let a comma b be an interior point of region R and a small neighborhood a plus h comma b plus k be a point in its neighborhood a comma b and lies inside R. Then first point is the point a comma b is called a point of relative or local minimum if f at a plus h comma b plus k is greater than equal to f of a comma b. For all h comma k, then fab, the value of function at a comma b, is called the relative or local minimum value. What is the meaning here? Suppose this is your closed and bounded domain and this is a function a comma b, the point a comma b, and it can have neighborhood here a plus h comma b plus k. If h is in here, h and k can be negative and positive any value. These are the neighborhood value. Because h and k are arbitrary values, so h, according to variation of h and k, we can change the value. If the value, we are taking the small neighborhood, the value at these points of the function fxy is greater than the value of this point, and these values are in neighborhood of a comma b, it means h and k are very small. But here I am taking both positive and negative, both I am taking. H can be negative also and h can be positive also. Similarly, k can be negative also, k can be positive also. So if the value of the function in the neighborhood of a comma b is greater than equal to the value of the function a comma b for all h comma k, then this point is called minimum. The point is called where we attain the minimum value, and the value is called minimum value. Point is called point of minima. Similarly, we can define for maxima also. Similarly, point 2, the point a comma b is called a point of relative or local maxima if the value in the neighborhood for arbitrary h comma k both are very small is less than equal to fa comma b for all h comma k. Then this value fab is called maximum value, relative maximum value. This is the definition of maxima and minima in sense of neighborhood point. Here I am not demanding the differentiability of the function, but this method is very difficult because in the neighborhood of a comma b infinitely many points exist. But this is the one approach to find the maxima and minima. Basically, this method is used to fail the maxima and minima at a comma b. Mostly. Some remarks we have. A function fxy may also attain its maximum or minimum value on the boundary of region. This is very important remark. One time Gate exam asked this type of question. I will discuss today in the problem session. Another notation is absolute maxima, or another word is global. Absolute or global. If we are interested in absolute maxima or global maxima, then it is a max value of all local maxima or relative maxima. If you are interested in global minima, then it is a minimum value of all local minimum. All local minimum values. Minimum values. Maximum values or relative maximum values. One important point. The point at which minimum or maximum value attain value of the function occur, also called point of extrema, point of extreme or stationary point. If you are getting maxima and minima at any point, then that point is called a stationary point. Here a comma b, we suppose the point of maxima or minima, then this is called a stationary point. And together maxima and minima is called extremum. If we call one important word here, minimum and maxima values taken together are called extreme values of the function or extremum of the function. Some people call optimum values. Optimum values. Another word, optimum values. Let's see one important condition. That is very important theorem. Necessary condition for a function to have maxima or minima. Necessary condition. These conditions are necessary. If these conditions are not satisfied by any function, then he will not attain maxima or minima. So these conditions are very important. Let the function fxy be continuous and possesses first order partial derivatives at a point P A comma B, then the necessary conditions for the existence of an extreme values, maxima or minimum values of F at the point P are partial derivative with respect to x of fab is 0 and partial derivative of f with respect to y at a comma b is 0. So these are the necessary conditions for the existence of extreme values or maximum of minimum values of a function. These conditions are also called critical values, critical points. But critical point is also collection of some other conditions also. So let's see the definition of critical point. If these conditions are not satisfied, a function cannot have maxima and minima. But if the function satisfies these conditions, it will not guarantee that the function has maxima or minima. But if these conditions fail, it is guaranteed that function does not have maxima or minima. So these are only necessary conditions. Critical points. This is the important definition. I have already discussed in one variable. A point P, A comma B, where partial derivative of f with respect to x and with respect to y are 0 is called a critical point or stationary point A point P A comma B is also called, this is the condition I have studied necessary, but some additional points are also called critical points. So let's see. A point P A comma B is also called critical point when one or more or both I am taking for two variables, both of the first order partial derivatives do not exist at point A comma B. If at this point A comma B, the first order partial derivative, both are 1, does not exist, then this point is also called critical point. So critical point is very important. If we have critical point, then we will get a important theorem that's called sufficient conditions for a functions to have a minimum and maximum. If these conditions are satisfied, function will have definitely maxima or minima. But in the sufficient condition, if these conditions are not satisfied, even though function can have maxima or minima. So let's see what are the sufficient conditions for a function to have an extremum or minimum or maximum value. Let a function fxy be continuous and possesses first and second order partial derivatives at the point PA comma B, means have first and second order partial derivatives at point A comma B. If PA comma B is a critical point, I have already discussed this definition, critical point, then the point P is a point of relative minimum or local minimum if RT minus S square greater than 0 and R greater than 0. It is a P is point of relative maximum if RT minus S square greater than 0 and R less than 0, where R is the second derivative of f with respect to x at a comma b, and s is the mixed derivative fxy at a comma b, and t is the second derivative of f with respect to y at a comma b. What about if rt minus s square is not greater than 0? When rt minus s square is 0, we have to investigate further. Further investigation is needed. In this GATE syllabus, I am not discussing it, but if someone is interested, he or she can personally discuss with me. If RT minus S square is less than 0, this is important, then the function f has no minimum or maximum value at this point A comma B. In this case, this point A comma B is called saddle point, where we did not attain maximum and minima. It's called saddle point. So what is the flow chart in two variable case to find maximum and minima? Let's see. First step, consider a function u is equal to fxy. Second, calculate x and y using fxy using del f by del x equal to 0 and del f by del y equal to 0. Third, let we get x equal to a and y equal to b from step 2. Then check RT minus S square for maxima and minima. 5. Now maximum and minimum value is given by f of a comma b. So let's see some examples, and after that we will see some previous year GATE question asked based on this topic. So example 1. Discuss the extremum of fxy is equal to u is equal to xy a minus x minus y. So u is equal to fxy is given you xy a minus x minus y. Now del u by del x or del f by del x meaning is same. So del u by del x is ay minus 2xy minus y square. del u by del y is ax minus x square minus 2xy. For critical points, we put del u by del x equal to 0 and del u by del y equal to 0. We can see that these two equations are symmetric in x and y. What is the meaning of symmetric in x and y? If we replace x in place of y, there will be no change. There will be no change. You will get another equation. It means x equal to y is a solution of these two equations. One solution is x equal to y. Now, what is the meaning of this? So we can put x equal to y and we can get two solutions here. So if we solve these two conditions for x and y, we get the critical points are, I'm not going in the solution, critical points are 0, 0, a comma 0, 0 comma a, and a by 3 comma a by 3. So one solution is x comma y, x equal to y, you can see from these 2 points. Now the working to check maxima and minima at one point will be similar for other 3 points. So at 0 comma 0 I am going to solve. Firstly I am going to solve second derivative del u by del x square. So if we differentiate it with respect to x again, we get minus 2y. So what is your r? R is del 2 uy over del x square at this critical point 0 comma 0 is 0 here. Del 2u over del x del y with respect to differentiate y, you will get a minus 2x minus 2y. So your s will be rst del 2u by del x del y at 0 0 is a here. If you del 2u by del y square with respect to y, if you differentiate it, you will get minus 2x and the value at 0 0 will be 0. So now if you find RT minus S square, RT minus S square, it is 0. RT minus S square is not 0 into 0 minus A square. So minus A square is less than 0. So 0 0 is saddle point, means at this point fx has neither maxima nor minima. At a comma 0 and 0 comma a, you can check that in the similar manner these are also saddle points. Now I'm going to check at a by 3 comma a by 3. So your r will be del 2u by del x square at a by 3 comma a by 3 is minus 2a by 3. S is your I have discussed S is your a minus and del 2u by del x del y was a minus 2x minus 2y. So del 2u over del x del y, that will be s at rt, t, your will be t, rst, s, sorry, rs, this is your s. Similarly, rst, remember this, a by 3 comma a by 3 is a minus 2a by 3 minus 2a by 3. So it is your minus a by 3. And similarly, you can find t, that is minus 2a by 3. Now rt minus s square will be your 4a square by 9 minus a by 3 square. So it is a square by 3, that is greater than 0, but r is negative. Rt minus s square is, r is negative, we cannot claim because nature of a is not giving. R can be negative also, R can be positive also, because it will depend the value of a. Here it is positive because a square. So if a is negative, if a is positive, then you will get maxima at a by 3 comma a by 3. If a is negative, then R will be positive. Then in that case, you will get a minima at a by 3 comma a by 3. So according to the nature of a, you will get the maxima and minima in this question. Let's see another example. This is a very important example. U is equal to xy plus a cube over x plus a cube over y. Discuss the maxima and minima. Discuss the maxima and minima, and A is giving you as a positive value. So del u by del x will be y minus a cube over x square. Del u by del y will be x minus a cube over y square. For critical points, del u by del x equal to 0 and del u by del y equal to 0. Now, y minus a cube by x square equal to 0 and x minus a cube by y square equal to 0. So you will get x square y equal to a cube here and x y square equal to a cube here. Compare both the equations. So x square y minus xy square equal to 0. If you differentiate, subtract, so y minus x equal to 0. So x equal to 0, y equal to 0 and x equal to y. But these conditions are not satisfied, because if x and y are 0, then this function is not defined. So the suitable condition is only x equal to y. Now you put x equal to y in any one of these two conditions. So x square into x equal to a cube. So x equal to a, similarly y equal to a. So the only critical point we have a comma a here. A comma a here. Now check the second derivative. Now check the second derivative. So del 2u by del x square is del 2u by del x square is 2a cube over x square. So r will be del 2u by del x square at a comma a, that will be the 2. Similarly, del 2u over del x del y will be your 1. So yes will be del 2 r st del x del y at a comma a, that is 1. And del 2u by del y square is 2a cube over y cube is there. Y cube is there. So del 2u by del y square at a comma a, that is your t, is again 2. Now check the Lagrange's condition. Rt minus s square is 4 minus 1 is 3 greater than 0. And r equal to 2 is greater than 0. So a comma a is point of minima. Point of minima. What is the minimum value? We will get the minimum value at a comma a. So minimum value will be fxy was xy plus a cube by x plus a cube by y. So faa will be a square plus a square plus a square is 3a square. So minimum value is 3a square and the point of minima is a comma a. I am giving you two questions as a homework. Try. First question, discuss the extremum of the function x cube plus y cube minus 3axy, and second is u equal to x square plus xy plus 3x plus 3y plus 5. Let's see some previous year question asked. The total cost CT of an equipment in the terms of the operation variable x and y is the optimal value, means extremum value, minimum or maximum value. You have to round it to one decimal place. So it is a two variable. You can see that there are x and y here, two variables. 2x plus 12,000 over xy plus y plus 5. I have discussed the same problem in the example 2. Now differentiate CT with respect to x. You will get 2 minus 12,000 over x square y. Del CT over del y, if you differentiate, you will get it is minus 12,000 over xy square plus 1. For critical points, del CT over del x equal to 0 and del CT over del y equal to 0. So you will get x square y equal to 24,000 from first equation, and you will get xy square equal to 12,000 from equation number 2. If you divide 1 by 2, or you can multiply 2, you can see that if you multiply here by 2, you will get 2xy square equal to 24,000. Now if you equate these two equations, so 2xy square equal to x square y, or if you take common xy, this is 2y minus x equal to 0. So you will get x equal to 0, y equal to 0 and 2y equal to x. This point is not acceptable because x and y are denominators. So only condition is 2y equal to x. This condition you can apply in any one of the conditions. So suppose we put in 1, x equal to 2y. So this will be 2y square into y equal to 24,000. 2y square. So it will be y cube equal to 6,000. If you take the cube root of y, you will get 28.8. Then you will get y. I think you will get here x square y. You are differentiating x square y, and this is 2xy square. Then if you take xy common, this is 2y minus x equal to 0. So x will be the 2y here. Okay. Now, yeah, here I did a mistake. I think this is 2x square y equal to 24,000. And it is 12,000 actually. 12,000. Make it correction here. And then it will be 2x square y equal to xy square. So it will be 2x minus y equal to 0. So the 2x equal to y, 2x equal to y. The another condition will be 2x equal to y. Here 2x square y equal to 12,000. Now it will become, if you put here, if you put 2x equal to y in the equation number 2, you can find the value of x very easily. Put y equal to 2. Yes. We get the second condition is 2x equal to y. Put y equal to 2x in the equation number 2. So it will give you x into 2x square equal to 12,000. So x cube will be your 3,000. Then x will be 14.4. So y is just double. So y is 28.8. So the critical point is your 14.4 comma 28.8. So the critical point A comma B you got now 14.4 comma 28.8. Now you will get maxima and minima at this value only. But the question is you are getting optimal value. It means you are getting here maxima or minima. And he is not interested in the nature. Means he is not interested in the maximum value or minimum value. Then there is no need to find the second derivative. You can get the value from this value only. So find the CT at 14.4 comma 28.8 just. So 2 into 14.4 plus 12,000 over, because you will get any nature maxima or minima at this point only, and he is not asking maxima and minima, he is asking just optimum value. That can be maxima and minima anyone. If you want, you can find the second derivative also. You can check, you can know the nature that optimal value is minimum value or maximum value. So if you calculate it, you will get this value is equal to 91.2. 91. So right now I don't know this optimum value is minimum value or maximum value because the question is not asking. Second problem is the function fxy equal to 2x square plus 2xy minus y cube has only one stationary point, only two stationary points. We have to get the stationary point. Stationary points are points where we attain maxima or minima, and saddle points are points where we did not attain maxima or minima. So let's check. Fx with respect to x, if we differentiate it, this is 4x plus 2y. Fy, this is 2x minus 3y square. So for critical points, fx equal to 0 and fy equal to 0. If you equate the critical point fx and fy to 0, you can find the solution of these two equations. So what will be the solution? 4x plus 2y equal to 0 and 2x minus 3y square equal to 0. If we solve these two equations, you can put x equal to put value of x in this equation 2. This is suppose 1. This is equation number 2. You can solve it for x and y. You will get two solutions: x equal to 0, y equal to 0. One root, and second is x equal to 1 by 6 and y is equal to minus 1 by 3. You will get 2 points here. But these are stationary point or not. For these, you have to check RT minus SS. Actually, these are critical points. These are stationary points. Both these are stationary points. Both these are stationary points. If some of these stationary points does not have maxima and minima, then that stationary point becomes saddle point. All are stationary points. Stationary points are critical points. These both are stationary points. It have another classification, saddle point, if some stationary point does not have maximum and minimum. So we will get two stationary point, but there is no need to check maximum and minima here. If the question is asked for saddle point, then we have to check. Saddle point is also type of stationary point. Problem 3. fxy is equal to x square minus y square. Then f with respect to x is 2x and fy with respect to y is minus 2y. For critical points, actually the point is given to you, but we are again going to find fy is equal to 0. So 2x equal to 0 and minus 2y equal to 0 means the point is 0, 0. Now I am going to find second derivative, del 2f by del x square. That will be 2. Del 2f by del x del y, that is 0. Del 2f over del y square, that is minus 2. At 0, 0, r will become 2, s is 0 and t is minus 2. Now rt minus s square, 2 minus 2 minus 0, this is minus 4, less than 0. It means 0, 0 is saddle point. Firstly 0, 0 what is stationary point, but now it becomes saddle point. Means neither maxima nor minima at 0, 0. At 0, 0. Problem 4. fxy equal to x square y minus 3xy plus 2y plus x. Now, with respect to x, it will be 2xy minus 3y plus 1. With respect to y, it will be x square minus 3x plus 1. Plus 1. For critical points. With respect to y, it will go 2. We will get 2 here. With respect to y, you will get 2 here. For critical point, fx equal to 0 and fy equal to 0. So 2xy minus 3y plus 1 equal to 0 and x square minus 3x plus 2 equal to 0. You will get x equal to 1 and 2 here, and you can put here. When x equal to 1, you will get the value of y. When x equal to 2, you get the value of y. Now put x equal to 1. If you put x equal to 1, your y will be 1. You can check it. If you put x equal to 1 here. And when you put x equal to 2, you will get y equal to minus 1. You will get y equal to minus. Now we have the critical points. So check the second derivative. Because we are interested in local maxima and local minima or relative maxima or relative. fx, second derivative with respect to x, this will be 2y. This will be the 2y. fxy, now differentiate it with respect to y, it will give you 2x minus 3. Now fyy, with respect to y, it will be 0. So at 1, 1, I am going to check at 1, 1. Then r will be, this is del 2f by del x square. At the critical point 1, 1, this is your 2. S will be the minus 1 if you check at 1, 1, and t is 0. So rt minus s square is minus 1. You can put the values, and this is less than 0. So this point is saddle point. We are not getting maxima or minimum. Similarly, you can check for this point. You will get again RT minus S square is less than 0. So no local extrema, no local extrema, because both the points are saddle point. At both the points, RT minus S square will be less than 0. Find the absolute. It means now you are interested in global maxima of the function. This is an important question. Fxy is equal to x square minus xy minus y square minus 6x plus 2. Fx with respect to x, 2x minus y minus 6. Fy with respect to y, that is minus x minus 2y minus x minus 2y. For critical points, Fx equal to 0 and F del with respect to y equal to 0. If you solve these two equations, 2x minus y minus 6 equal to 0 and minus x minus 2y equal to 0. If you solve these two equations, you will get x equal to 12 by 5 and y is equal to minus 6 by 5. Now find second derivative. Fxx with respect to x, it is 2. Fxy, it is minus. Fyy, this is minus. Now 8, 12 comma 5 and minus 6 comma 5. R is 2. S is minus 1. T is minus 2. RT minus S square is minus 4 minus 1, that is minus 5 less than 0. So saddle point. It means this point is a saddle point. But you are in rectangular plane. That is a closed and bounded plane. I told you one remark. What was that remark? Remember, this is a very important remark. Maximum and minimum can be attained at the boundary point also. So for the rectangular plane, you have to draw a bounded region here. Now if you draw the bounded region, you can see that the value of x is between 0 to 5. I am taking up to 0, 5 and y is from minus 3 to 0. So this is your rectangular plate here. This coordinate is 0 comma 0. This is 5 comma 0. This is 0 comma minus 3. This is 5 comma minus 3. So for the closed and bounded region, we have to check at the boundary point also. Now check the value at 0, 0, at 5 comma 0, at 0 comma minus 3. This work I have to did for the bounded region also. For the bounded region only. Because in that region we know the points are boundary point or the corner point. So at 0, 0 the value is 2. The value is 2. If you put x and y equal to 0. At 0 comma minus 3 value is minus 7. At 5 comma 0 value is minus 3 and 5 comma minus 3 value is 3. So the maximum value is attaining here. So this is your absolute maximum. Absolute maximum is 3 and point of maxima is 5 comma minus 3 and this is the minimum value. So this is the absolute minimum. Absolute minimum value, minimum value is minus 7 and the point of minima is 0 comma minus 3. This work I have to do when the region is bounded. Next problem is the continuous function fxy is said to be saddle point. What is the saddle point? RT minus s square is less than 0. R means del 2f by del x square at a comma b. T is del 2f over del y square at a comma b. Minus s is del 2f over del x del y at a comma b whole square. Is less than 0. Check the condition where I am getting this point. The C option is correct. C option is correct. And first critical point condition is compulsory. This can only we can proceed when necessary conditions are satisfied. Then only we can go for sufficient condition. For the sufficient condition, necessary condition is given there that we have critical points. The next problem is, that's a very important problem and favorite for next years. The distance of the origin, the point nearest on the surface. Suppose we have a 3D surface and we want the distance from origin, nearest distance. This distance can be nearest. I don't know the nearest distance. Suppose this is the nearest distance and the point is x comma y comma z because we are in 3D plane. So this is suppose O point and this is your P point. Then OP distance is under root x square plus y square plus z square. Now the nature of square root function, if it is a positive function, and if we do square both the side, suppose that is d square x square plus y square plus z square. The nature of d and d square will be same. If d is attaining maxima at any point, then d square will also attain maxima at that point. Similarly for minima also. Suppose this d square is f. So f equal to x square plus y square plus z square means now we have to minimize this function because nearest point is asked. Nearest means minimum distance is asked. But we have studied up to for only 2 variables. For the 3 variables, we have a Lagrange's multiplier method. But I did not discuss this method because in the GATE syllabus, this method is not very useful or not asked any time. So here the condition between z and x and y is given, that is surface. And because the point P is satisfying the surface z square equal to 1 plus xy, so it will obviously satisfy. It means we can put the value of z square at 1 plus x into y. Now this is a 2 variable first question and we can proceed it. Fx is 2x plus y. Fy is 2y plus x. For critical points, fx is 0 and fy is equal to 0. If you do equal to 0, 2x plus y equal to 0 and 2y plus equal to 0, the only point is 0 comma 0. Now you get 0 comma 0 is x comma y. So what will be the z or z is 1 square equal to 1 plus xy, and this point is satisfying the surface. So z square is 1 plus 0, it means z equal to 1 or minus 1 or minus 1, 1 or minus 1. So the point P can be 0, 0, 1 or 0, 0, minus 1. So the distance will be d will be the under root x square plus y square plus z square. It means the distance will be 0, 0, 1. The point is 0, 0, 1. So distance will be 0, 0 plus 1 chi square or 1. Similarly, if you take minus 1, then again you will get distance is 1. So the minimum distance is 1. The minimum distance is 1, and the point where I am getting the distance, the point of minima are 2 here, 0, 0 plus minus 1, and the distance is 1. The next question is the given function fxy is equal to 4x square plus 6y square minus 8x minus 4y plus 8. We have to see the maximum minimum value. Fx is 8x minus 8. Fy is 12y minus 4. For critical points, Fx equal to 0 and Fy equal to 0, you will get x equal to 1 and y equal to 1 by 3. So this is the point, critical point. Now Fxx, second derivative is 8. Fxy is 0. Fyy is 12. So at 1 comma 1 by 3, r is your 8, s is 0 and t is 12. Now check rt minus s square, that is 96 minus 0 is 96 positive, and r is also positive. So minima at 1 comma 1 by 3. So we have minimum at 1 comma 1 by 3. Now the problem is how to find the minimum value. You just put 1 comma 1 by 3 in the function, you will get the minimum value. If you put x equal to 1 and y equal to 1 by 3, the minimum value you will get 10 by 3. The minimum value is 10 by 3. So this is your maxima and minima here. The minimum value is 10 by 3. So from my side, several variable calculus, differential calculus is over. In next lecture, we will study the multiple integrals. Multiple integral is very important topic, and we did not discuss here Lagrange's multiplier method. If someone is interested, he or she can read that. That is also important topic for academics, and sometimes very useful to solve in difficult problems of maximum and minimum. Okay, thank you.